This project was done for Professor Keith Benedict, who is ill this semester, but anyway, he's a gun enthusiast, and he was interested in seeing what the reliability of a pin-fire cartridge was in terms of alignment of where it would strike the pin, or the fire. The pin would strike the cartridge to fire it. Craig and Nick took on the project and had to basically do a fixture and set up the testing program to find out basically what Keith needed to know. So here's the project.
Thank you, Professor Sprouls. As he said, I'm Craig Jochem. This is Nick Campbell, and our project is determination of the firing pin alignment reliability on a center fire cartridge. The question arose, if firing pin doesn't hit the center on the primer, will it still go off? Or if it does, how far off center you can still hit and it be reliable? The objective of our project was to determine how far off center you can hit and find out where that reliability drops off, if it drops off at all. We needed to create a fixture that would hold a case, drop a firing pin on the primer, and also be able to move the firing pin around to hit different locations on the primer and be able to accurately measure where exactly we are hitting on the primer.
Okay, to understand our project, you need to understand how firearms work and how the bullet is fired. The picture on the left here is a backside of a 44 Magnum center fire cartridge. The primer is indicated in the center, which is set inside the casing. The picture on the right is of a firing pin, and this is the actual piece that when the trigger is pulled, the firing pin comes forward and strikes the primer and ignites the bullet. Center fire ammunition is popular because it can be, the primers in cases can be removed, and bullets can be reloaded into the cases. They can be reused.
This is a model of kind of give you an idea of what all a cartridge consists of. It consists of the case, primer, the gunpowder, and the bullet. The primer is inserted on the back side of the case next to the rim. And when the primer is struck with the firing pin, it shoots a spark into the gunpowder, which ignites the gunpowder and causes explosion and propels the bullet out into the gun.
So our given problem was when a firing pin, it could become misaligned, and this could cause misfire with the primers, which is simply when the primer is struck, but it's not struck well enough that it ignites, and basically your bullet does not fire.
Our project goal was to determine at what point does a misalignment of a firing pin striking a primer become unreliable. Here's a picture of some of our test cases. The one on the left is a case where the firing pin hit the primer in the center of the primer. The one on the right is where the firing pin hit the primer on the edge. These are kind of outermost limits of our experiment, and it just kind of gives you an idea so you can see the difference.
Some useful information. The 44 Magnum cartridge uses a large pistol primer, which has a 210,000 diameter. The firing pins that hit them are only 73 thousandths. And there is a variation of the center of the primer from the center of the case, which is only 1,000th, which we were able to measure. We measured 20 cases, and then we compared them to information on ammunition manufacturers' websites. And 1,000th of an inch is the average width of a human hair, so it's very small.
Here's just some case dimensions for a 44 Magnum case. The overall length is 1 and 285 thousandths. The diameter of the rim, which is on the left side of the picture, is 514 thousandths. The case diameter nearest the rim is 457 thousandths, whereas on the other end, away from the rim, the case diameter is 456 thousandths. Now, the reason for this is when you load the bullet into the gun, into the case, you have to trim down the end of the case to provide a good seal for when the primer goes off and the explosion happens, just so it's a good seal to launch a bullet at a consistent velocity.
For our project deliverables, there was no method to test this, so we had to design and build a testing fixture that would strike the 44-ounce cartridge. The fixture had to be able to move at very small, precise increments of 7/1000th of an inch. What Craig is passing out is a metal shim that is 5 thousandths thick, so this gives you a little bit of an idea of how small it was. Our data needed to be collected into, organized into a graph file, so it's easy to read.
If you guys could pass those shims around, just we'll collect them at the end of the presentation.
And what you see here is a Birmingham manual mill in the Applied Engineering Center. We chose this to be our platform for our testing fixture. The reason is that the chamber block that we had could be mounted on the vise on the table, and the table used to give us our precision movements that we needed. The mill has digital readouts on it, so it's accurate within 0.5 of an inch. And we were able to use the shaft where the tools are normally held in the mill. Just with gravity, just drop a firing pin through the shaft, and that would strike our cartridge. And this worked extremely well for what we wanted, and we were able to do all this without really purchasing additional equipment.
Here's our chamber block. The picture on the left, the hole in the middle, is what we considered our chamber. This is where we placed the case when we went to go test it. And here is our actual chamber block. Just to give you an idea on how big it actually is. We did mill a slot into the side just for easy removal of the case after it was tested. We drilled and ringed out the chamber to 460 thousandths. We made just a few thousandths over what the case diameter is, just so it would be easy to remove. We did drill it in a specific spot on the block so we could come back to find where exactly the center of that circle is very easily. The picture on the right shows some relief holes we drilled into it just to help expel some extra gases when the primer is set off, just to make it a little safer.
Have our firing pin here. We turned it down from a piece of 4140 tool steel stock, and we used a manual lathe, and the picture on the left shows the pin. We turned it down and then used a hand file to file it to the correct roundness that was needed. Too round and it wouldn't, too blunt and it wouldn't set off the primers, but if it was too sharp, it would just puncture them and it wouldn't set them off either. So it had to be pretty close. The flat edge on the firing pin is for there's a set screw in the shaft in the mill, and we used that. That was the easiest way to give us a smooth fall through the shaft without it hanging up and affecting our results. And the right side is a picture. It is drilled and tapped. We had a support rod that was screwed into the back, and the support rod just basically gave it extra weight and allowed it to stay straight through the mill. We guided it through the mill.
Here's pictures of our support rod. Our support rod was made out of 1/2-inch hot rolled steel ground bar. On the very end, we turned it down for 1/2-inch 13 threads, which would match the tapped hole in the end of the firing pin. And as you can see on the right, it screws right on. After we made it, we figured out that the shaft in the mill was actually just a hair under 1/2-inch thick, so our support rod wouldn't work. So we had to come up with a different solution for this problem. Our solution was to use all thread. The all thread actually worked better because we could use nuts and washers to change the weight and play with the weight a lot more than what we could with the round bar. The nuts were just small enough to slide through the shaft easily, but they were big enough to also prove to have support inside the shaft, so it wouldn't wobble and wouldn't allow the firing pin to come down crooked. The washers were easy to add and subtract weight real quick, and it actually proved a lot better than the round stock. For testing, we had to first square up the vise to the mill, so we used an indicator right across the face of the vise and made sure that it was squared to the mill. Then we set the chamber block on parallels and clamped it down. We tapped the chamber block down just to make sure that it was parallel so that it wasn't cocking in ways that would hinder our results. We then used an edge finder to find the corner of our chamber block that we marked to come off of for where the center of our hole would be, and that proved to work just fine because when we went to testing, it was right on center right away. We then inserted the all thread through the shaft and screwed it onto the firing pin, and with the 2 jam nuts, we were able to have a piece of sheet metal with a notch cut in it that we could just remove real quick, and the firing pin would just drop right through, which worked real well. We had one person that would pull for every test just to make sure that it was consistent throughout the whole testing. And when we finally found the right weight, we wanted to make sure that we got 10 consistent ignitions of the primer in the center of the primer in a row, just to make sure that we had the right weight and we didn't have any flaws. Here's a video of our test. You can see here on the edge of our chamber block our relief holes, and the firing pin will drop through the shaft and hit the primer. So it's a lot to see, so I'll show you the video twice. Have a video then. Pretty much a video, you could see gases coming out of the relief hole. You would actually see a flame. So it was real loud, and with all the gases coming out, we made sure that we wore safety glasses and hearing protection just to stay safe through the project.
Okay. This is a graph of our results. On the left side, we have the y-axis. It is on a scale of 0 to 10. This is our successful fires for each set. And on the x-axis on the bottom is distance from the center across the radius of the primer. So we start at 0 and at 7,000 increments all the way out to 63 thousandths, which Craig has some of our cases.
Pass that down too.
One is struck in the center, the other is struck on the 60,000 mark. Gives you an idea of the distance that we traveled across it. The blue line is our expected results, which we expected 10 out of 10 until 42 thousandths. We expected it to fall off really fast. Red line here is our actual test results, and we achieved 9 out of 10s until 28 thousandths, where we achieved a 10 out of 10. And after 35 thousandths, the reliability really steeply fell off. And this was simply because we were nearing the edge of the case, or the edge of the primer, and it took more force there to find the primer.
Although we didn't get perfect 10 out of 10 on the first couple tests, we do believe that it could have been because the cases with the primers in them were not stored in a dehumidified room in between when they were assembled and when they were tested. Some moisture could have gotten the primers, which could have hindered their results. We made sure that every primer we tested, if they didn't go off with the first initial hit, we took a hammer and hit the end of the firing pin and just hit it with more force, and every primer that was tested did go off. So we still got the result that we were looking for. There was a steep drop-off after 35 thousandths off-center. So we did get the result that we were looking for, and we were happy with the results that we got. We would like to thank Keith Benedict, Eric Sprouls, Donna Moore, Dr. Julian Davis, Dr. Zane Mitchell, and Barry Plastics for help with our project through this semester. Are there any questions?
You want me to just project? I'm pretty good.
Okay.
I've seen some test results on 9mm and, oh. Okay. I've seen some test results on 9mm. One question I have is not so much it was off-center fire, but it was how many pounds you were hitting it with. Did you have any results on as far as how many pounds you were using, pounds of force?
We did calculate how much force we were using. We did see that, we did look up where they were using 100 inch ounces of force on the normal firing pins, what they suggest. So we didn't quite look up what we were hitting with, but we figured if we were hitting center, we just kind of moved up to where we barely got enough, and then that way we could, if we had just enough of the middle, that once we got out to the edge, you could see that there would be a drop off.
Right, you were trying to make sure that it was just barely enough force
Yeah.
to strike it. I think it would have been interesting if you used different levels of force, and you might have got some other graphs.
Yeah.
You know, were you always using the same brand and type of cartridge and primer?
Yes, but they were all, the cases were bought in one bulk package. Primer was bought in one bulk package. They were all assembled on the same day, and they were all the same brand. So
That's one of the things with ammunition. They talk about soft and hard primers and how hard you have to strike them. So
we did think about that before we started, but we only have so much time to test, and there's so many different kinds of primers that you could use.
you have to
We just
limit
stuck with
the
one primer,
scope.
one case, and just went with that.
Okay.
All right, other questions? Let's see. So how many did you actually put through the system in setting things up and then running your experiment?
We probably went through about 50 to 100 tests just to find the right height and weight to drop on it. But then once we finally said, this is our height, this is our weight, we did 10 sets of 10 for another 100.
Okay, so it took a little while
Yeah.
to get there.
It took about 4 hours.
Right.
But once we got going, it was just put them in and drop, put them in and drop. It was real quick.
Okay. Any other questions? Let's give them a hand.